Hello, my name is Elijah Andrews, and this is my lab report for Lab 1 charged tapes. The purpose of this lab was to calculate the charge of two pieces of office tape that we polarized by ripping them up off of another piece. The main principles we'll be using in this report are electric fields and a little bit of momentum principle. The results that we found were that the tape charge was 1.4 times 10 to the negative 6 coulombs. However, we had to borrow another team's data in order to calculate this. The main principle that we'll be looking at is electric fields. The electric field at a given observation point is determined by multiplying the charge of the source item by the electric constant and multiplying that by the distance away and dividing by distance squared. The way we calculate the force caused by this electric field is by multiplying that electric field vector by the charge of the receiving item. The way we did this experiment was first by charging the strips of tape by putting them on another piece of tape and ripping them off, and then checking how these charged pieces of tape interact with objects such as our hands and positively charged pens. We then use this data to calculate what the approximate charge of each tape is. In the lab, after we charged the tapes, we measured how it interacted with other objects. So for example, as you can see on the right, the tape was attracted to a positively charged pen, which means that the tape itself is negatively charged. However, the two pieces of tape were actually attracted to each other, which doesn't make sense if both of them are supposed to be negatively charged. And you can see we attempted to do the floating tape experiment, but were not successful. Using the data from my friend of their tape length of 52 centimeters and their distance between the two tapes of 6 centimeters, we can calculate the charge of the two pieces of tape. We know that the net force in the y direction is equal to 0 because the force of gravity on the upper tape is being counteracted by the electric field and it is stationary, so there's no movement. By setting the force of gravity equal to the force of electric field, we can solve for Q. So I plugged that equation as well as the constants into GlowScript and used that to calculate Q, which I found to be 1.4 times 10 to the negative 6 coulombs. For the second part of the lab, I determined the approximate fraction of atoms that gave up electrons. So I divided the charge of each piece of tape by the electron constant to get the number of electrons, then divided the area of the piece of tape by the approximate area of an electron, and ended up getting a ratio of 9 times 10 to the negative 7th electrons per atom, which makes sense given that tape is not particularly conductive. The two most likely sources of error are the charge transferring from people holding the tape to the tape, meaning that it's no longer negatively charged, as well as potential rounding errors throughout the lab. These are a couple of the further questions. What if electrons are positive and protons were negative? The charges of everything would be flipped, but the actual interactions themselves would be the same because it doesn't matter what the charges are of the particles that are transferred, it just matters that they are transferred. And the reason why we try to handle the tapes as little as possible is because handling them is likely to cause charges to transfer and neutralize the tapes. Thank you for your time.